So, as we start discussing the applications of integrals and the applications of integration, I wanted to revisit the fundamental theorem of calculus for a little bit, mainly because uh, we need to tweak a little bit how we look at the fundamental theorem of calculus to really make applications easier to approach. So our fundamental theorem of calculus, remember, came in two parts. The first part establishes that derivatives and integrals are inverse operations of each other. So if I take the derivative of an integral, I get the integrand. And if I take the integral of the derivative, I get the original function. So part one is just saying derivatives undo integrals and integrals undo derivatives. Part two is what allowed us to evaluate definite integrals. And that's the idea that if I find the antiderivative of the integrand, plug in the upper bound, plug in the lower bound, and then subtract them. If we think about it, the fact that we have a separate notation for the antiderivative can be a little bit confusing. So we can also choose to rewrite this where I can phrase it as, well, if I'm taking the integral of the derivative, it's the antiderivative of the derivative is the original function. Plug in upper bound, plug in lower bound, and subtract. This is a much more useful way of thinking about integration, is that we're doing a definite integral of a derivative, at least when we're talking applications. So I had another teacher that told me that she calls this FTC with a twist, and it's a very nice name for it. Just evaluating a definite integral, the way it's written, FTC part 2, works great. But when we do applications, the FTC with a twist is a little bit better. And the idea of this is we take part 2 and we isolate f of b. So we're actually going to ignore this notation here. And I'm going to get f of b by itself. So I'm going to add f of a to both sides. So f of b is now by itself. That's going to be equal to f of a plus the integral from a to b of f prime of x dx. Why this is useful for us is in a real life situation, f of a is the starting value. F of b, I should probably use a different color for that. F of b is the ending value. And that means that f prime, I already used that color, is my rate of change. Instantaneous, but remember, I don't really need to say the word instantaneous. It's assumed when I just say rate of change. So if I want to find, because a lot of times in applications, we know the value that something starts at, we know the rate of change for it, and we want to find where it ends at. So the FTC with a twist gives us an easier approach to this, and that if I want to find an ending value, I take the starting value and add on the integral of the rate of change. What that now means is that the integral of the rate of change accumulates the rate of change to give us the net change. And that idea of accumulating is central to this entire unit and should make sense, because if you think about it, the integral notation is shorthand for a summation. It's adding up a bunch of stuff. So the idea here is we're adding up a bunch of infinitesimally small rates of change to get the net change. I spell change correctly. So the integral of the accumulator is going to be the overarching concept in this unit, in that we are thinking of this as the integral accumulates things. Anytime in calculus I want to accumulate something, I'm doing the integral. So we can accumulate the instantaneous rate of change to get the net change. An example of this is if I accumulate instantaneous velocities, I can get displacement. If I accumulate speed, I can get distance. If I accumulate jerk, I get acceleration. If I accumulate acceleration, I get velocity. But this also then, we're going to revisit RAM. And remember, the idea of RAM is we want to add up an infinite number of those rectangles to find an area or to estimate an integral, but integrals can be interpreted as related to area. So if I accumulate the areas of rectangles, I get area. And then we're going to look at 3 dimensions, and if we accumulate cross sections of solids, we're going to get volumes. And that's kind of, if there's nothing else out of kind of the videos for this first section that you get, the big idea you need is when we want to accumulate things, we're going to use an integral to act as the accumulator.